Okay, let's talk about integral calculus, section 1.3. So the most important thing that you're going to need to be able to do is integrate your functions, because we're going to have vector fields. And let's say if I go back to an example of a vector field here, let's find a better one. Okay, let's go to this one. Here's your vector field. Let's say you start here and then you make a path, and you go there and you travel through the field that way. What you care about is, as you go through this path, you care about the field, okay, these lines that are parallel with your motion at that time. So we're going to take the dot product of, let's say, as we walk through here, of this field vector with our location vector at any point. Okay, so if we travel as we go out, we travel at right angles this way for a second, we're going to experience no field if we stay in a circle that's always perpendicular to those field lines, because the dot product of our location vector and this vector gives you 0. But if there's a spot where you are going this way, then you're going to feel the full force of that, and your dot product is going to be full. So, if you walk this way, you can do just force times distance, for example. If you walk this way, you can know that it's 0. But for the case that you walk this way and then that way, and then you follow a path like that, or you follow a path that looks like this, where your path is y equals x squared or something like that, if we have a coordinate system x, y, then you need to know how are we going to integrate along this thing, add up the dot product at every little point. So we're going to calculate the dot product of this with our position vector and add it up to that, and this, and add it up to there, and add it up, and so on. And we gotta have a way to do that, and that's what calculus allows us to do, is just add up a bunch of little bits in a way that makes it easy. So if you want to integrate a line, a path through a vector field, you take the integral of your vector field dotted into your location, your little infinitesimal walking along that line, your line bit, and you integrate from A to B. Okay, V is just the vector of the field vector. DL is your little displacement as you walk, and you're comparing the two vectors together and taking the dot product of the vector field and your DL line at each point. So you want the component of the vector field along your displacement vector as you walk along the line, okay? So that's all we're doing there, is adding up a bunch of dot products along your path. And if you take a complete path, circle around something, then that's what this circle means. It's just an integral over a closed loop, okay? And that's what that signal represents. From A to B, you took a path from A to B, and you want to add up all the dot products along that path. Okay, so an example of that is if you, in free fall, your force is constant, so you don't worry about it, and your displacement vector is constant in terms of the direction, so it's just force times distance. But if you pull something at that force and you move this way, you want the dot product F dot dl. So let's say you're applying a force on a thing, and you pull this way for a little while, and you travel a little distance, and then you pull that way for a little while, then you travel a little distance, and then you pull this way. Okay, you need to add up F dot dl for this distance, plus F dot dl for that distance, plus F dot dl for that distance, and that would be your total work. Or if you are just constantly changing your force that whole time, now you need to do the integral, so you don't have to actually calculate every little bit of line. So here you go, here's your path. You're adding up all your little DLs dotted into all your little vector fields on the path you're taking. Now, the important thing is, most of the time, if you integrate from A to B, it turns out that for most of the forces we deal with, conservative forces, the path doesn't matter. You don't really care about the integrating the actual path, and you only really care about integrating the endpoints, the function, evaluating the function at b and a if you can get the integral of it, the integral of the function itself. Okay, so here's an example. If you have this vector field y squared in the x hat direction, 2x y plus 1 in the y hat direction, and you want to calculate what the line integral is along a path, that actually two paths, over and up or straight over. So in order to do that, you just take your little dl thing is just going to be your dl dotting into dl is just dx x hat, dy y hat, dz z hat, because that is just representing your the components. You're just always moving a little bit in the x, a little bit in the y, a little bit in the z. Okay, and so that's what your infinitesimal line thing is, and you dot that into your vector, and then that gives you how the path is changing. Okay, so if we want to do the horizontal segment, then that path, we're going to move in the x direction. Y is going to be 1 because it doesn't change. It stays at 1 that whole time. And then, so v dot dl is just y squared dx. And then y is 1, so that just gives you dx. So if we integrate over that line, we just integrate from 1 to 2, dx equals 1. So it's just 1. 1 times 1, 2. Okay, so we get, let me erase this. My pencil's not working quite right. All right, so on the vertical stretch, dx and dz are 0 because we're not changing anything in the x direction, we're not changing anything in the z direction. So our dl vector just becomes dy y hat. X is 2 because we're at x is 2 for that run as we move straight up. So then v dot dl is just, our v is, y squared x hat. So if we do v dot dl, these are both vectors, is equal to y squared, okay, hold on, eraser, okay, is y squared x hat plus 2x times y plus 1 y hat dotted into just dy y hat. Okay, so if we do that, we get y squared x hat times dy y hat plus 2x times y plus 1 y hat dotted into dy y hat. Okay, so the y hat dots gives you 1, this gives you 0. You end up with 2x times y plus 1 dy. So you get 2x y plus 1 dy. Simplify that, you get 4 times y plus 1. I delete that because x is 2. And then you get, if you integrate then v dot dl, you integrate 4 times y plus 1 from 1 to 2, and you get 10 if you do that. Okay, so if you take path 1, you get 11. If you take path 2, you do the same thing, you get 10. Okay, so, or sorry, yeah, you get 10. Okay, so then for the loop that goes out 1 and then back 2, you go out 11, come back 10, you get 1. Okay, so in this case, this is a path-dependent integral. The path you take gives you a different answer. So this is an example of a non-conservative path, for example, with a non-conservative force. Most of the time we deal with conservative forces, so your path doesn't matter, but this is an example of how the path you take does give you a different answer. Okay, so those are line integrals. Those are, you're integrating over a line. And now for surface integrals, we have the integral of v dot dA. Now we're integrating over a surface, and when we integrate over a surface, what you care about is you're literally adding up this area, okay, and then you're dotting it into the vectors that are coming through the surface. So what you care about is, instead of the vector field being, you're taking a path and the vector field is like this, and you want to know your little line segment dotted into that path at every point. Now you've got a vector field moving through a surface, and so you've got a vector field spreading out like that, and then you say, okay, how much vector field is flowing through the surface? So you take the area, and then what you care about, you don't care about the component of the vector field this way, parallel with the surface. You want the vector component perpendicular to the surface. So you take the dot product of the area, which is normal to the surface, dotted into the vector. And so this v dot dA is your vector field dotted into your perpendicular vector representing the surface. Okay, and so what would that look like? If your area dA perpendicular to the surface is in the z hat direction, then dA vector is just z hat. Okay, it's just the in the direction of the perpendicular. If it's in the z hat, if your surface is like this and it's in the y direction, then your dA is just the y hat direction. If your surface is like this, okay, and it's got a little bit of a component in the x and the z, or the y and the z, then your dA is going to be some amount x, or x hat, we'll just say x hat plus y hat, or it could be x hat plus z hat, or whatever. Or if it's at some weird angle, it might be 2x hat plus y hat, or whatever. So your dA is usually straight up or down, or you can force it to be straight up or down or something like that. So then it's just in the z hat direction. So you only care about if your vector field is 2x hat plus 3y hat plus 4z hat, but then your area, your surface area, is just in the z direction. Well, the component of this, the components in the x and y hat direction don't contribute anything to your dot product, so v dotted into dA is just going to be 4z hat dotted into z hat, so it's just going to be 4, it would be dz in this case, but z dot z would give you 1. So then the only component you care about are your vector field that's actually contributing to your answer is the z hat component if your surface that it's traveling through that you care about is in the z direction, right? So this gets a little complicated if you have a circle, a surface like that, and then your vector field is coming out like this. Then it actually gets simpler this way, because that you can use some symmetry to say that this is the same across the whole surface. So then your vector times the surface area, 4/3 pi r cubed or whatever it is, will give you your answer dotted into it. So you can see it though how this is why you need an integral, because if your surface looks like this and your vector field looks like that, then you're going to want to model this function and get some polynomial or whatever, dot that into your surface, or that becomes your surface, then you're going to want to dot that into your vector field. And so you can see how your area, your dA, might be a function of x, y, and z if it's not just a nice flat plane. Okay, so the idea here is that if your vector field describes a flow of fluid, for example, then v dot dA represents the total going through that surface, which is called flux. Okay. Yeah, so let's go through that. So we got an example of, here's your surface, and at any point on the surface it has a vector dA which is pointing normal to it. In this case, this dA vector would have components in the y and the z direction. So dA would be something like 1 y hat plus 1 z hat, something like that. Because it doesn't look like it has anything in the x hat, but if it did have something in the x hat, well, let's just add an x hat to it. So then when you're dotting it into stuff, you only take the components that are perpendicular to that line. Okay, so there's an example here. Calculate the surface integral of this function through this cube in figure 123. So this function, whatever it looks like, let's see if I can bring up Desmos, no, not Desmos, 3D, no, Math 3D, boom. Okay, and let's see if it works on this iPad. Okay, so, let's get rid of this surface. Let's add a vector field, and let's make the vector field 2xz, 2x times z for in the x-hat direction. Let's see if I can 2, and then we want x plus 2 in the y-hat direction, and then we want y times z, where is my caret? Shift 2, okay, and minus 3, and we can get rid of this bottom normalization thing, and let's see, parentheses expected, okay, add a parentheses, c squared minus 3, there it goes, boom. Okay, so let's take a look at this vector field. Ooh, fancy. Okay, so that's what it looks like. So there's stuff going every which way, it looks like. Let's do from 2 to 2 to 2. We've got oops. So this, our x is from 0. Hello. Value expected 0. Oh, for God's sakes. Oh my gosh. 0, comma 2. Let's try this again. And 0, comma 2. And 0, comma 2. Done. Okay, so there's our, look at that, beautiful. Look at this, beautiful. Okay, so that is our vector field flowing through this cube 2 by 2 by 2. You guys see that? Okay, so there's our cube 2 by 2 by 2. That corresponds to this cube, and what we're trying to figure out is what is the flow through each side. What is the total flow through each of these surfaces? This face, that face, that face. We're trying to add up all the components there. Okay, look at how cool that is. This is really cool. Okay, so what do? We want to calculate the surface integral. We want to integrate the amount of flow coming out of each one of these surfaces. So this dA vector is in the x direction. This dA vector is in the y direction. This dA vector is in the z direction. So those are very simple vectors. So then all we have to do, we know that x is 2. So dA is just in the x-hat direction. So then v dot dA is just 2xz times dy dz, which is 4z dy dz. And so if you want to do that dot product, just v dot dA. The surface is in this x, well, in this case, this surface is a combination across this here. So that's your x and z plane. Sorry, that's y and z. Y and z will give you that surface area. Okay, so then you dot that in there, and you just, there's your integral. It's simple. So there's 16, whatever the unit is. It could be, some flow rate is coming out of it. So remember, a dot product gives you a scalar, so then we just integrate, we get a number. And the let's see, face 2, which is out the back side of this, out here, coming towards me. You can see there's no flow going towards the negative x direction. Okay, you can see that pretty clearly. That's kind of amazing, right? So no flow going in the negative x direction, so you get 0, and that's what it looks like. Y equals 2 for the third face, so this face coming out that way. Third face, just do that integral, you get 12, and so on, minus 12. So you can see in the positive y direction, you get a huge amount of flow. That is, positive y direction. In area 4, it's the same amount but negative, right? It's going through the surface is positive 12, out the other surface is negative 12. because it's going into the surface. If you have a surface like this and the flow goes into it, that's negative. If it's coming out of it, then it's positive. That's just a definition we use. Okay, so then your total flux through all of the sides, 16 plus 12 minus 12 plus 4 equals 20. So you have a net flow in this cube. And if you can see that here, your flow isn't coming evenly out. It's coming in one side, out the other. So you have a net positive flow of 20 through this surfaces. It's not perfectly balanced coming out of there. So that's just pretty beautiful. Okay, so then your volume integral is going to be the same thing. Your surface integral is just like a line integral, and then your volume integral is going to be some, function over a volume element, and a typical volume element is dx, dy, dz, because volume is length times width times height. So now you're integrating over a volume. So if, for example, T is the density of a substance, then your integral of your volume over this little area would just be, your volume, not volume, but your, I don't know what he's referring to as this little v here. But anyway, that's your vector function, the x component of it, the y component of it, the z component dotted into d tau. So then, look at that, you just break it up into the x, y, and z components. So volume integrals are pretty easy. Because the dot product only gives you the x, only gives you the y, only gives you the z, and if it's x, y, and z, and there's no y component in the x component and so on, then you end up breaking it into three vectors, so that makes it easy. Okay, and so for example, calculate the volume integral of t equals x, y, z squared over the prism in figure 1.24. So we've got a prism here, okay, and we want to integrate. We've got this density function, let's say, that the density is changing as a function of location. So at x equals 1 and z and y equals 0, let's see, at x equals 1, and yeah, so at any of these edge points, you're going to have 0, and it's going to have kind of the most density at the highest z, but also a non-zero x and y. So it's going to get more dense as you get higher up, I guess. So we want to integrate our function from 0 to 3 in the z direction, and then we want to integrate it from 0 to 1 in the y direction and 0 to 1 in the x direction over all three volumes. And then our function is x, y, z squared. So you just do these three integrals all at once, and I don't know, you get 3/8, whatever that is. Okay, so that might be the mass if t is the density. So 3/8 would be the total mass of this thing. Okay, so you're just doing three integrals over the three spots, and it just takes a little practice doing this to get a sense of what you're doing. Okay, so we've got some examples there, or problems to do. Okay, so the fundamental theorem of calculus just says that the integral of a function is equal to the value of the function, the integral of the derivative of a function is equal to the value of the function at its endpoints that you want to calculate the derivative. Okay, and that makes sense. If you have a velocity versus time graph and you go from v0 to v final, and you look at the acceleration versus time graph at that time, the constant acceleration time, the area of this graph is at, and that tells you at the endpoint your value there is equal to the integral of this function. Okay, so acceleration times time, v final is equal to v initial plus at. You're adding the area of the acceleration versus time graph to get your final velocity there, and this is what this is saying. The integral of this function is equal to the value of the function at its endpoint. This would be the integral of that acceleration versus time function. This would be the derivative, and the derivative of this function is a constant, a, namely, and that's all the fundamental theorem of calculus says. Okay, so what it means for gradients, though, is pretty cool. So for gradients, here it is, the gradient of a function, which is just the derivative, dotted into dl, your line element, is just equal to the value of the function at its endpoints, just like normal. So if you take a gradient of a vector field or a scalar function or whatever, the important thing is that the integral of a gradient is independent of the path taken. Okay, that's a really important thing. It doesn't matter what path you take, the integral is the same. A closed loop, since it's a conservative force, a closed loop or a conservative field or whatever, a closed loop gives you 0. Okay, because the beginning and end points are identical, so t at point B would be the same as t at point A, and so as you go around, you come back to where you start, that line integral is going to be 0. So if t equals xy squared, then check these two things. So you take, there's your infinitesimal line element. You want to move in the x, y, and z directions all at once, and then your gradient would be y squared x hat plus 2xy y hat. And so then do your function. Y is 0. Your dl component then is only in the x hat direction, so your gradient dotted into dl, dotted into the dl thing, just gives you y squared dx, and that equals 0. So your gradient dotted into dl equals 0 for that first section, and then for the next section, do the same thing, and you get this equals 2, and so you can see the total line integral is 2, and bink bink, you do it again for a different path, you also get 2, bink, and just to show you that it's correct. Okay, so that's pretty cool. Let's see, and then for divergences, this is a pretty cool thing too. So for divergences, the fundamental theorem says that the integral of the divergence of a vector field through a volume, like as flow is coming out of a volume, it's equal to the integral of the vector field through the surface. So that basically says that however much, what this relates to is the flow out of a point is equal to the flow through a surface. Okay, so that relates the two. If you add up all the vector fields in a volume going through a surface, they're the same. And that makes sense. So if you know how much water is coming out of your hose, you should measure the same amount of water going through a screen, for example. So this is the amount of water coming out of your hose. That's the amount of water traveling through an area at a given point. And you can set them equal to each other. We're going to use this one all the time because we can relate the charge here to the field it generates. And so we can say that the amount of charge in this area is equal to the amount of electric field lines flowing through a surface. So we're going to use that all the time. Okay, so get a sense of that. So that's called Gauss's law or Gauss's theorem or the divergence theorem. And here he's saying if you add up all the faucets in a volume, then you can measure the amount of water going through a surface, and that's basically what it is. So you can check that theorem using this function, and again we can draw that function here if you want to see what that vector field looks like, and then take your divergence of it, del dot v, and do your calculation, and you get that this equals 2. You can do the same thing, add everything up for through each surface element, and you get 2. Okay, so either way you do it, you get 2, so they're equal to each other. So work through that just to make sure you're understanding it. And then same thing for curls. This is called the circulation. Del cross v is equal to the line integral around a surface. So the curl in a volume or around a surface is equal to the line around the perimeter of a patch. Okay, and that's called the circulation. So that's saying that the curl in this surface is equal to the curl is equal to if you just integrate around a closed path around the perimeter. Okay, and that's called Stokes's theorem. Okay, so it depends. So this del cross A dot dA depends only on the boundary line, not on the surface used. You can go around any way around and you get the same answer. And then same thing is 0 for any closed surface. Okay, so blah blah blah. Yeah, there's an example here. Do some integrals. So do this one just to get some practice. Make sure you're able to do these integrals. And then the last thing here is integration by parts. Integration by parts just relates the integrals, and actually integration by parts comes from doing the integral of the product rule. So product rule says the derivative of two functions is first derivative of the second plus second derivative of the first, where first is f, second is g. So we say first derivative of the second plus second derivative of the first, right? And okay, so you get this thing for the product rule. So we want to say that the integral of some function f times the derivative of some function is equal to, this is the result that we're going to use. Okay, so we have to put our function in this form first. So let's say we want to evaluate this integral. So this is f and this is g. Okay, and what we're going to do then is take the derivative of that, and the derivative of that here is looks like the derivative of e to the minus x. Okay, so the derivative of the derivative of e to the minus x dx is equal to minus e to the minus x, right? So then e to the minus x is equal to the derivative of minus e to the minus x dx. Okay, so we're saying that this is g, and so then we get that's d of g. dg dx gives us this one. Okay, so that's how we're defining our variables there. And so then there's our e to the minus x. We're writing it as the derivative of a function so that we can have it in this form, f times the derivative of a function. So then the integral of f times the derivative of this function is just equal to, and we plug everything in here, g, which is e to the minus x, well actually minus e to the minus x, and then dx, and because the derivative of df dx is just 1, and then we know this one gives us 1, so that's how you'd solve an integral like that via integration by parts. Okay, and then you have some product rules here, or exploitation of the product rules in the same way there, and we'll just use those for special cases. Some nice little rules about the relationship between derivatives of functions and then how they relate to the line integrals. Okay, but when we encounter them, we'll deal with them. All right, talk to you guys later. Bye.